Okay, so we've developed all of the machinery we need to be able to put together a one-dimensional solver. So for this next set of two sections, what we'll be doing is first I'll ask a couple questions about what we might expect to be interested in, and then we'll switch out to an example linear 1D solver using the techniques we've developed and investigate some of these questions. I'm not going to be able to give a definitive answer for every single possible physical situation, but I would recommend that you play around with either the solver you've written yourself, or at the very least the example solver code that will be provided alongside of this, and see what you can do to explore some of these questions, because these questions, while they certainly are relevant for our linear 1D solver, have broader applicability for really any situation where you're attempting to solve a PDE numerically. So the first thing that we'll think about is H convergence. So what we mean by H convergence is when we refine our global domain into more and more elements. So we can imagine pathological example being where our whole entire domain is just one element, and then two elements, then we continue to subdivide and add more and more elements. Now, we would expect that as we continue to add elements, our solution should converge until eventually, once we've added sufficient elements, it should be within machine precision of the exact solution. And this seems like a reasonable assumption, assuming that the function is well behaved. So the question is, how quickly would this solution approximation converge as we vary our element size? So we would expect that the rate of convergence might have something to do with the underlying nature of our solution approximation. So in this case, we're using linear piecewise polynomials, so we would think that perhaps there's something to do with that nature, and that perhaps if we were to look at higher order solution approximations, that perhaps convergence might be different. And so we'll examine that later on in Module 3. The other question we might ask ourselves is, how coarse can our elements be and still get a good enough answer? So that's all well and good to try to get to within machine precision of the analytical result, but frequently we don't need that degree of accuracy. Ideally, especially in complicated cases where maybe we're not looking at a linear 1D situation, but maybe a full-blown complicated 3D situation, it's going to be very expensive computationally. So we want to just get good enough. So as in sort of a playground, how good can we get to our exact solution with a minimum number of elements? And then finally, what effect does the shape or smoothness of the solution have on convergence? So we're sort of implicitly assuming that a piecewise linear solution approximation is going to be able to properly capture the analytical solution. And so for smooth functions, that seems kind of reasonable, right? If we have some sort of function, we can represent this quite well with piecewise polynomials. But now imagine that we were to instead have maybe large discontinuities, or maybe we would have situations where we'd have very large gradients. In this case, then, especially where we have something like large second derivatives, our linear approximation might not do a very good job, especially you could imagine here, where especially if you think about a feature of the solution is smaller than the element itself, we're not going to be able to capture that very well at all. So we can specify different initial conditions in our solver and see how the solver behaves and handles those different possibilities. The other thing we can examine with regards to convergence is the size of our time step. So as we previously discussed, we would expect that if we make delta t too big, then potentially we're stepping too far into time such that our current behavior is not going to be representative of that whole time step. Another thing that we can think about is, imagine we have some sort of periodic solution. So in other words, whatever we have flowing out wraps around and comes back in. If we're properly conserving, would we expect that the overall solution would stay steady with respect to time? Certainly over short time scales it makes sense, but if we were to let this thing run for 10, 20, 30 seconds, 10 hours, 10 days, would it stay this constant? And then finally, how does the interplay between our step size for our elements and our step size for our time discretization, how do they interrelate? So let's switch over to the example linear 1D solver and play around with a couple of these things.